explained tropicalization in the first lecture. Every variety whatsoever can be tropicalized, we agree, and you can compute that in GFAN, and a little bit maybe in Macaulay too tomorrow. So now that we understand tropicalization, let's try to understand discriminants and resultants, so that by the end of the day, all three words in the title have been defined. So, for instance, for a cubic polynomial in one variable that has 4 coefficients, so an unknown is t, the discriminant is this polynomial delta, 27x1 squared, x4 squared, and so on. So it's a polynomial in 4 unknowns of degree 4, having 5 terms. So the Newton polytope is in 4-dimensional space, but really it lies in a plane. If you plot the Newton polytope, it's a quadrangle with one point in the relative interior, and there are the vertices. So the Newton polytope, the discriminant, is a quadrangle. So in general, we're defining the notion of the A discriminant. And throughout A will be an integer d by n matrix. I will assume that the matrix has maximal row rank d. So I will assume, these are technical hypotheses, that the rows are linearly independent. And I'm also going to assume that the all-one vector is in the row space of A. Now, such a matrix A represents a family of hypersurfaces in D space, defined by the Laurent polynomial that has n monomials, that has n terms, one for each column of the matrix. And the coefficients, it's a family because the coefficients are unknown. So I have unknown coefficients, x1 up to xn. And just like over there, so the cubic polynomial on the right slide would be an example with d, well, okay, would be an example with n equals 4. So here we have a Laurent polynomial with n terms in d unknowns, t1 up to td, and the coefficients x1 up to xn are unknowns, parameters. Now I'm going to be interested in the hypersurface that's defined by this polynomial, and we're going to look at the hypersurface in the torus C star to the D. So I'm going to look at the complex points, but as I said, you could replace C here by another algebraically closed field characteristic 0. So let's consider the hypersurface, and we're interested in the condition on the coefficients such that the hypersurface has a singular point. So for random, for generic choices of these coefficients xi, this hypersurface will be smooth, and there's some special condition on x1 up to xn, which happens when the hypersurface acquires a singularity. So for instance here, this cubic polynomial defines the hypersurface on the line. So it defines 4 points on the line. So it's a 0-dimensional smooth hypersurface on the line. And then 2 points, when 2 points come together, then this hypersurface has acquired a singularity, so not just numbers, also other things can fail to be smooth. And so we get the discriminant, which is the condition on the coefficients for this to happen. So the closure of this set is an irreducible projective variety in Pn-1. It's denoted by delta A, and it's called the A discriminant. So the A discriminant, so the matrix A describes a family of hypersurfaces given by a polynomial with n terms. I'm interested in the condition when there is a singularity. Now, the way I phrased it, it's actually not a closed condition, so you have to take the closure. The closure is an irreducible variety, denoted delta A, and it's irreducible. You have to think for a moment. So the way I set it up, it's irreducible over spec Z. Okay, so it's defined, or can be defined over the integers, and we call this the A discriminant. So in many cases, often, but not always, the discriminant will be a hypersurface. So often, but not always, it's a hypersurface. Now, if it's irreducible and if it's a hypersurface, then it's going to be defined by unique, up to sign, irreducible polynomial of content 1, and I will also call that the A discriminant. So in the codimension 1 case, I'm going to use the term A discriminant either for the hypersurface or for its defining polynomial, which is unique up to sign. Okay. Depends only on the matrix A. And C is a field, algebraically closed field of characteristics 0. So here's an even simpler example. So let's take the family of Calabi-Yau zerofolds defined by this one-dimensional reflexive polytope. So last year you all heard about reflexive polytopes. So here's a one-dimensional reflexive polytope defining a family of Calabi-Yau zerofolds, and this is its discriminant. Okay, so F is a binary form x1 t2 squared plus x2 t1 t2 plus x3 t1 squared. The discriminant delta A is unique up to sign, and it's x2 squared minus 4 x1 x3. Now I'm going to go through a sequence of examples. Most of the talk now will be a sequence of examples, and I will always write a matrix, and please check that my hypothesis is always satisfied. So always my matrix will have linearly independent rows, and the all one vector will be in the row space. And I'm always going to plot a picture of the columns. So the columns 0, 2, 1, 1, 2, 0 are the black dots, right? So the columns are 3 points on a line. So that's the picture. So I'm always going to write the matrix. I'm going to draw a picture. So in this case, we have this little 3 black points. Those are the 3 columns. And they form a one-dimensional convex polytope. Now, how do you compute the A discriminant? So, for instance, in Macaulay 2, and I think we're going to see this tomorrow morning. So, well, we're interested on the condition, right, that the hypersurface has a singularity. So, let's look at this family, and let's write down the partial derivatives of f. It has d partial derivatives. Now, remember, the all one vector being in the row space is sort of saying that the polynomial is homogeneous. So I'm going to write down its Jacobian ideal. I'm going to just write down the ideal of its derivatives. df dt1 up to df dtd. So this is an ideal in d plus n variables. Now I'm going to pick a monomial order that makes the t's, t1 up to td, very, very expensive. I really want to get rid of these t's. They're very high. And x1 up to xn is very, very low. So for instance, a lexicographic monomial order. And then I say Grobner, right? So I eliminate t1 up to td. And then on the screen, you will see the polynomial. In the codimension 1 case, like over there, you'll see the polynomial, which is the A discriminant. It's just there are no more t's. It only has x1 up to xn. And I wrote try it tonight or maybe tomorrow morning. So for instance here, the way we calculate a delta A, so we don't know delta A, the condition. So how can we find delta A in this case, right? So this is the condition for a quadratic polynomial in one variable to have a double root. But there are 2 ways of deriving this polynomial. Either you remember the quadratic formula from high school, right? So the quadratic formula says that the t is actually, the solution is actually an algebraic function in x1, x2, x3. And there's some formula that you can actually write it down. So, you know, there's something involving plus minus the square root of something. So you can write down the two roots if you remember the formula. And then the condition is, you know, that the two roots are the same. And then you get this expression. Or you don't remember, like me, you know, you don't remember anything from high school. Then you have to do this algorithm. So you take the partial of f with respect to t1. And then you have to take the partial of f with respect to t2. That gives you a system of two equations in 5 unknowns, right? x1, x2, x3, and t1 and t2. You eliminate t1 and t2, and you get the discriminant. So that works in general. Okay, next example. So keep in mind, I will always draw the picture, and the picture is always the configuration of column vectors in each case. Okay, let's try this. So here, d equals 3, n equals 6. So I take this matrix, this 3 by 6 matrix, which some of us struggled with right after lunch. And that's the picture. Right? So I get the picture is, I get this configuration of 6 points in the plane. So let's calculate the discriminant. So this is a family of surfaces. Right? This is a family of surfaces given by a single polynomial f in 3 unknowns, t1, t2, t3, with, you know, with 6 coefficients. So there's the family. So this represents this family of surfaces. Again, x1 up to x6 are the unknown coefficients. And then these t monomials, they're just the columns of the matrix A. Right? So the first column, 0, 1, 0, gives the t2. And the last column, 2, 0, 1, gives t1 squared, t3. Okay, so let's do this. So to compute the A discriminant, we take derivatives. We take the 3 partial derivatives with respect to t1, t2, and t3. Now notice what happens in this example. As we take partial derivatives, this is actually, you know, linear in t2 and linear in t3. And t2 and t3 drop out. If we take dd, you know, derivative with respect to t2 and derivative with respect to t3, then it only depends on t1. And t2 and t3 only appear in the first one. So when we do this elimination, actually we only have to look at the last two. Right? So now we eliminate the t's from this system. And the answer is the Sylvester result. So this is the discriminant in this case is a certain polynomial homogeneous of degree 4 in x1, x2, x3, x4, x5, x6. And if you expand it, this polynomial will have 7 terms. That's called the Sylvester result. Now, if you don't remember the Sylvester result, maybe you remember the quadratic formula, right? So it's the thing with the square root. And so it's the condition for 2 quadratic polynomials in one variable to share common root. And that's given by this polynomial.
What's the difference between the Cauchy resultant and the Sylvester resultant?
Pardon me?
Is there a relation between the Cauchy resultant and the Sylvester?
Very good question. So the resultant is this polynomial. When people use a name in front of it, they're talking about a matrix representation. So this polynomial with 7 terms is the Sylvester resultant, but there are different ways of writing it in a determinantal form. One due to Sylvester, one due to Cauchy, one due to Bézout, and maybe other. Okay? So when people talk about the Bézout resultant, or the Macaulay resultant, or the whatever, the Dickenstein resultant, then what they mean is a matrix formula, essentially, whose determinant you take, and then you get the polynomial we're interested in. Okay, so by now you should be able to draw its tropical hypersurface, right? So every polynomial gives a tropical hypersurface, so in particular this one, gives a nice tropical hypersurface. But the punchline of this example is actually a different one. The punchline I like to make is that discriminants and resultants are like the chicken and the egg. Right? What I've shown here is that the resultant is a very special case of the discriminant. If I pick my matrix A to be this rectangular box up there, I get the resultant. So the resultant is a very special case of a discriminant. On the other hand, we learned, when we first learned about discriminants, well, it's the resultant of f and f prime, right? So the discriminant is a specialization of the resultant, right? And so on. So which comes first? Well, I don't know, So there's the discriminant. Discriminant spawns resultant. Resultant spawns discriminant, and so on. So in these lectures, I'm going to take the point of view that resultants are special cases of discriminants.
Do you have a resultant?
Pardon me?
Do you have a resultant?
A resultant?
Yes.
Yes. Yes.
So that's the previous A?
No. I might come to that later. Yes. It's a child form of a toric line. Okay, so in these lectures I'm going to take the point of view that resultants are special cases of discriminants. So now we're in good shape, right? Because all the ingredients that we need for these lectures are in place, right? The lectures are titled Discriminants, Resultants, and their Tropicalization. So now we know about discriminants, about resultants, and about tropicalization. So now we're ready to go. Well, let me show one example of a variety of an A where we don't get codimension 1. So determinantal varieties, determinantal varieties can be seen as a special case of A discriminants. So let's take this matrix A. So if D is 4 and is 6, let's look at this matrix A over here. What's the picture? Our favorite picture, right? So this is the Toblerone. Right? So this matrix A represents the product of a red two-dimensional simplex and a blue one-dimensional simplex, and these are the 6 columns of this matrix. That clear? Yeah. So I have 6 points in 4 space. But they lie in a 3-plane, right? Some of the last coordinates, 2 coordinates is 1, and that's the picture. That's the Toblerone example. Now, what's the family of hypersurfaces? Well, it's a family of bilinear forms, right? Actually, I artificially add one more row to make it more symmetric. So the way to write this is f is a bilinear polynomial. It's linear in T1 and T2, blue, and it's linear in T3, T4, T5, and then I organize the coefficients as this 2×3 matrix, and that's a bilinear form. So that's the family of bilinear forms, and that's represented by a product of 2 simplices. So if I have a product of 2 simplices, such as in the Toblerone, then I get a bilinear form. 2 simplices give me a bilinear form. Now in this case, the discriminant has codimension 2, right? So when does this acquire a singularity? Well, the A discriminant in this example is the codimension 2 variety of all rank 1 matrices. So this acquires a singularity if and only if the coefficient matrix drops rank. But for a 2 by 3 matrix to drop rank, that's not a codimension 1 condition, right? The 2 by 3 matrix does not have a determinant. It has 3 2 by 2 determinants that cut out our discriminant, which has codimension 2. Okay, let's talk about the example everybody has been waiting for. Elliptic curves. So, an elliptic curve is a member of this family. So I take the family of homogeneous cubic polynomials in 3 unknowns, T1, T2, and T3. A is this 3 by 10 matrix, and that's the picture. So there's the picture labeled by x1 up to x10. So this is the family of elliptic curves. Now my elliptic curves have 10 coefficients. Okay? I take all cubic polynomials, homogeneous cubic polynomials, no Weierstrass normal form. Okay? No Weierstrass normal form. I take the full, complete family of elliptic curves. An elliptic curve, from this point of view, is a homogeneous cubic polynomial, dense cubic, with 10 unknown coefficients. Now why no Weierstrass normal form? To retain the symmetry. I like to retain the full combinatorial structure of the situation. I do not want Schirnhausen transformations or Weierstrass normal forms or any of these things to mess up my combinatorics. So that's why cubic polynomial has 10 terms. The family of cubic polynomial has 10 terms. Okay? We type it in, we run it, right? So the discriminant is a polynomial of degree 12 in 10 unknowns, x1 up to x10, which vanishes if and only if the plane cubic that's defined by that polynomial has a singular point and, becomes genus 0. Right? So requires a singularity. This is a polynomial with 2040 terms. So the discriminant delta A is a polynomial in 10 unknowns having 2040 monomials of degree 12. And it's that object I'm interested in. Tropical geometry, maybe side remarks. So there are many, many aspects of tropical geometry. One researcher who has made a very, very wonderful contribution to this field is Grisha Mikalkin from Toronto, who used the tropical approach to compute Gromov-Witten invariants. And that's, of course, the first Gromov-Witten invariant. So 12 is the number of rational cubics for 8 points, and that's the degree. Okay, let's do one more example. So I'm interested in this polynomial. Each and every one of these 2040 monomials and their coefficients are dear to my heart. Okay? I like to look at every single term in this expansion. Okay, let's look at hyperdeterminants. So I just said that if we take the product of two simplices, a red and the blue simplex, that represents a family of bilinear forms. Now if we take a product of three simplices, then this will represent the family of trilinear forms. So for instance, the three-dimensional cube, indicated by three colors, black, blue, and red, is the direct product of three one-dimensional simplices, and that represents this family F. So that's the family of trilinear forms, and that's a polynomial with 8 terms in these t's. Here's the discriminant. And this is called the hyperdeterminant. This is the 2 by 2 by 2 hyperdeterminant. Right? So this is the determinant of this 2 by 2 by 2 matrix of coefficients. So you look at this polynomial. This is a certain polynomial of degree 4 in 8 unknowns, having 12 terms, each one dear to my heart, and that's the expansion. Right? So you can see, the symmetry. It's very symmetric, has a very nice structure. This is the 2 by 2 by 2 hyperdeterminant. It vanishes if and only if this trilinear hypersurface F acquires a singularity. Now this is sort of a famous polynomial, in physics, this polynomial is called the tangle, and it measures, entanglement of quantum states. So this is the determinant of a 2 by 2 by 2 tensor. It's known as the tangle. Computer scientists would call this, a situation with 3 qubits. Statisticians call this a table, 2 by 2 by 2 table. So in any case, we're taking the determinant of this 2 by 2 by 2 table, and that's what we get. Just for the fun of it, let's do the 4 cube. Are there any questions? Maybe I should pause. This would be a good moment to pause for a question. So is there any question about the discriminant of the family, full family of elliptic curves, or about the hyperdeterminant of a 2 by 2 by 2 matrix?
Where do you use the condition on A when you decide?
Where do I use it? Okay, that's a very good question. I want my polynomials to be homogeneous. I don't, strictly speaking, I don't really need it. It's a technical hypothesis that makes some of the things a little easier. So in the background, I'm not going to tell you, but there's sort of a toric variety in the back of my mind, and I want this to be a projective toric variety rather than an affine. I like things to be homogeneous and projective. So it's sort of a hypothesis that makes the theory a little easier. Okay, ready for the 2 by 2 by 2 by 2 determinant? Okay, let's go for it. Okay, so a product of 2 simplices represents a family of bilinear forms. A product of 3 simplices represents a family of trilinear forms. And here we have now, I don't know what you call these, 4 multilinear forms and 4 groups of variables. So there is the polynomial. So we have a 5 by 16 matrix whose columns are the homogeneous coordinates for the 16 vertices of the 4-dimensional cube, and that's the family F. And again, we have the color coding for the groups of variables. So here A is the 4 cube. Okay, so the A discriminant, delta A, is the hyperdeterminant of this 2 by 2 by 2 by 2 tensor. This is a polynomial of degree 24 in the 16 unknowns. In this 4-qubit system. And if we expand it as a polynomial, if over there we have the complete expansion. So here the number of monomials is 2,894,276. So, and each dear to my heart. So that is the 2 by 2 by 2 by 2 by 2 by 2 by 2 hyperdeterminant. Now, really, somebody had a conversation over lunch with one of the graduate students, and I noticed that there was another person from the same department. I said, oh, I saw, there's you from this institution, and then there's this other person. I said, oh, we don't know each other. I'm in applied math, and he is in pure math. Really, this is a talk in applied math, but in the back of my mind, when I think about these 2 by 2 by 2 tables, I have some certain statistics and biology in the back of my mind, but well, here, the rest of mathematics serves a different role. So, can you draw the Newton polytope? Can you actually draw the Newton polytope? So, it's actually not so bad, right? Most of these monomials are not vertices on the Newton polytope. It's going to be an 11-dimensional Newton polytope, but only a tiny fraction of the monomials are going to be vertices. Only 25,448 of these monomials are vertices. And that's a very nice little, 11-dimensional polytope. And Josephine, who sits over there, can draw it for you in case you fail to draw it. Okay, so that's sort of a bunch of examples.
I'm sorry.
Yes?
How do you count those vertices?
Pardon me?
How do you count those vertices?
How do I count the vertices? Okay, so the vertices, so I take the convex hull of these 2 million terms, and a vertex is a 0-dimensional face, so it's a single point at which a linear functional, w, attains its minimum. So, here's an algorithm, right? So let me be Dan Bernstein. I really believe in randomized algorithms, so I'm going to pick, a billion times a random weight vector w in R16. It's going to take a minimum, pick a minimum. I do this a billion times, and the ones who make it are 25,844. That's a bad algorithm, but that would be one algorithm.
Do you know that you have that many monomials because you computed the polynomial? Or
Yes, I computed the polynomial.
So is there a way to know how many monomials there will be? Without
No, you have to actually compute it. There's a so-called formula, goes back to a Swiss mathematician, as like many good Swiss things today. So Schläfli in the 1860s had a formula, and that's actually so I'm going to talk in a minute about this book by Gelfand, Kapranov, and Zelevinsky, and that's the very last section of the very last chapter of this book by Gelfand, Kapranov, and Zelevinsky deals with Schläfli's formula for this polynomial, and all we did was to expand his formula. But it's a little bit of work involved. No, question?
So you randomize, how do you know that they're all?
I don't. You have to do something else. There's software for dealing with polytopes. I mean, in a way, the point I like to make in these lectures is that polytopes are actually easier than polynomials. So there's actually, software for polytopes, which we will not demonstrate, and there's software for polynomials, such as Macaulay 2, and, eventually they all not terminate, but polytopes usually you can go a little further than polynomials. Okay, so I've given you lots of examples. The 3-cube, the Toblerone, the resultant, the hyperdeterminant, the family of elliptic curves. I could go on and on and on and on and on. But they're actually kind of bad examples. So what is actually wrong with all of these examples? What's wrong with these examples? For me, personally. Now, I find these examples misleading because they're too easy. They're actually a little bit too easy. And as a result of that, they're misleading. Now, that's crazy, right? I mean, are you crazy? I mean, what do you mean they're too easy, right? That looks pretty complicated to me. I mean, this is a polynomial with, 2 million terms. Can't be easy, right? It's hard. We struggled to expand it, and Schläfli, had a hard time. So, what do you mean they're too easy? I mean the following. In each of these examples, the underlying toric variety is smooth. The underlying toric variety in each of these examples is a projective space or a product of projective spaces. So in the Toblerone, it's a product of 2 projective spaces, P1 times P2. In the hyperdeterminant, it's a P1 times P1 times P1. In each of these examples, the polytope is simple and smooth. And in a smooth case, we have a lot of algebraic geometry at our disposal. We're in the situation that Mike described this morning. We have, we have nice formulas for Chern classes and so on. So there's a lot of easy, sort of well-developed machinery for smooth algebraic varieties, in this case the underlying toric varieties, that breaks down if the toric variety is not smooth. Now, in applications of algebraic geometry, and this is trademark of the special year called Applications of Algebraic Geometry at the IMA, Institute for Mathematics and its Applications in Minnesota. So there'll be a whole year on applications of algebraic geometry. We are faced with arbitrary matrices A. And in those applications, the A will generally not come from a smooth toric variety. We have to develop these computations. We want to do these kind of computations not just for nice, simple, smooth polytopes like the 4 cube, but for any old matrix A. Okay, right, but didn't these guys do it? So there's this work by Gelfand, Kapranov, and Zelavinsky. They wrote a book about these discriminants, arbitrary matrices A. Surely you're talking about old results that are 15 years old, right? Okay, so Gelfand, Kapranov, and Zelavinsky published a book called Discriminants, Resultants, and Multidimensional Determinants. It's a green book, and it appeared in 1994. And let me summarize some of the results, the key results in this book. First, this is a mild exaggeration, but all classical resultants and discriminants are A discriminants for various choices of A. So the classical multidimensional resultants and multidimensional discriminants, including all the examples that we've seen, these easy examples, they can all be gotten out of the A formulism for suitable choice of matrix A. True? The main object of interest in their book, the key insight that they had, is that yes, you should try to compute the discriminant, but more so, you should try to compute the Newton polytope of the discriminant. The discriminant itself is sort of a complicated object, but maybe you can get your hand on the Newton polytope. And they have a theorem that says the Newton polytope, delta A, is a Minkowski summand of another polytope, which they constructed, called the so-called secondary polytope. I'm not going to define the secondary polytope. Suffice it to say there's a beautiful self-contained combinatorial theory involving triangulations that leads to this secondary polytope. And the reason they introduced the secondary polytope is because they would want it to get at the Newton polytope of the discriminant. And summand is in the sense of my first lecture this morning. So, I have P plus Q. So P is a summand of P plus Q. Now, do they get the Newton polytope of the discriminant? Well, in particular, once you know the Newton polytope, of course, you know the degree of the polynomial, which they were very interested in. So what they gave is an alternating degree formula for the discriminant in the special case when the toric variety is smooth. So, in this example, on the 4 cube, the degree 24, that was known ahead of time. So there is an easy Chern class calculation on P1 times P1 times P1 times P1 that gives the number 24. That says, this discriminant, you don't have to expand this polynomial, you don't have to compute this polynomial. We know ahead of time that this degree, is 24. And it's given by a certain alternating formula. Plus something, minus something, plus something, minus something. So it's a certain Euler characteristic type situation where the number 24 is an alternating sum of positive integers. Now, from the point of view of combinatorics, alternating the formulas are unsatisfactory. What is more satisfactory is to have a positive formula. You would like to say 24 is a sum of this positive number plus this positive number, each of which counts something. So for instance, the breakthrough in McCulkin's work was, he said, the Gromov-Witten numbers of, surfaces, toric surfaces, is some number, right? This number 12, but it's the sum of some positive number plus some positive number, and every term can be explained. So positive formulas are better than alternating formulas. And again, they had the special case in which the toric variety is smooth. They get an alternating degree form. Now, a drawback, if you ever studied this book, the techniques are quite advanced, let's say, and they give little information when the underlying toric variety is not smooth, or when the codimension of the discriminant is bigger than 1. In fact, it's an open problem to characterize this case. We've seen an example where the codimension dropped to 2, and understanding when this special phenomenon happens at the current time cannot be solved completely by their methods. So what we would like to have is we would like to be able to, for instance, compute the degree of the discriminant and decide whether it has codimension 1 regardless of any smoothness hypothesis for any integer matrix A. So the answer in some sense is it's a fantastic book that I very much recommend. And they raise the questions that we're dealing with here, that we're discussing in these lectures. And they certainly raised the right questions, namely, what is the Newton polynomial of the discriminant? And they gave some very nice partial answers and almost complete answers in the smooth case, but unfortunately not when either the toric variety is not smooth or the discriminant is not a hypersurface. Okay, this is my last slide, so I'm going to actually end a little early today. People like to go to return, and maybe I'll borrow a little time and go overtime tomorrow. So let me give you an example of a situation that appears in practice in applications of algebraic geometry that I like to solve. And that's the example that you read in the announcement of these lectures. It's exactly the same example, our running example. That's the question of what is the degree of a mixed discriminant. So by a mixed discriminant, it's a polynomial that characterizes systems of S equations and S unknowns that have a double root. For instance, let's say, so in this case, this will be a single polynomial. So for instance, right, you might have 2 cubic curves in the plane, right, 2 elliptic curves. Now, generally, they're going to meet in 9 points. But for special coefficients, they may meet in 8 or fewer points. That condition is characterized by some big polynomial in 20 unknowns, the 10 coefficients from the first polynomial, and another 10 from the second polynomial. That's a special case. This kind of mixed discriminant, again, can be modeled by a suitable choice of A, and in general, it is not known what is the degree of such a discriminant, and I'm hoping that maybe in the discussions with the group we might make a little progress, and we might hear a little bit about this on Wednesday morning. So an example of this is this A. So here's a typical example, of a matrix A. That's our running example. So that's our 4 by 8 matrix. So the way this is built is that the first 2 rows are random big integers. We just put some big integers in the first 2 rows. And then the second row is, well, you know, I have this sort of block structure, right? I pick the 1s and then the 0s on the other side. And what I'm going to discuss in the next, I'm going to come back to this example. And there is an A discriminant associated to this. I will come back to what it means and how to compute it. And that's a typical situation where we do not get a formula from the GKZ book. And we will need new techniques. And these new techniques are tropicalization. So what we're going to do in the next lecture is we will compute the tropicalization of this discriminant and then a posteriori infer the degree. Okay, questions?
Is much known about what polytope you have the sum with the Newton polytope to get the secondary polytope?
Very good question. Sum is known. Yeah, it's a simple answer. It's basically a facial. So yeah, so let me give you the answer. So you have this polytope. I lost my lab. So we ate it actually. I had one more Toblerone about it. We had this working session. So you have this polytope and it has a discriminant. But every face of it is also a polytope and has a discriminant. So roughly speaking, and this is sort of false in general, but roughly speaking, what you do is you take the Minkowski sum of the Newton polytopes of all discriminants over all faces of A.
Can you take a desingularization of the historic variety or something like this?
Yeah, you can, but I don't think it really that the dual variety maps in gracefully. Right? So if you take another way of defining this delta A, it's the dual variety in the sense of projective geometry. It's a projective dual, and if you desingularize a variety, so the dual variety has to do with the sort of with the projective geometry in the embedded space. But if you desingularize, you're going to a different space and you don't retain much information. So it doesn't seem to help.
This is related to the first question. Somehow I missed what you were saying before. Did you say in the GKZ approach, the secondary polytope is easier to compute?
Much easier.
Okay.
It's bigger and easier to compute.
I see. So it's in fact the inverse problem.
That's correct. We like to solve the problem of Minkowski subtraction.
I see. That's the problem about which you said something is known? Or?
That's what I'm going to talk about. What I will do is I'm going to present a different approach. So in the next lecture, I will. What I'm going to do is the following. I will say, good news. If you're interested in discriminants and their Newton polytopes, you do not actually have to read this hard book. There will be a different self-contained approach presented in the next 50 minutes of lectures, purely based on tropicalization. So all you need is what I have described in the first lecture this morning, together with these definitions, and you will get a general positive degree formula for any discriminant delta A, regardless, no hypothesis.
Okay, any more questions? Okay, thank you.